Hi everyone. Due to the snow day, I decided to record the second half of my lectures on costs. I altered these slides to include additional math and graphs that I would normally reserve for the chalkboard in class. As always, feel free to email me or come by my office if you have any questions. In the previous class, we discussed total cost as a function of capital and labor. In particular, we analyzed a total cost function in which total cost equals fixed cost plus variable cost. Alternatively, we can have total cost be a function of quantity. As such, total cost depends on how much output the firm produces as opposed to the amount of workers that the firm employs and the number of machines that the firm owns. An example of this alternative way of specifying total cost is Q squared plus 10. Note that CQ means that the total cost function C is in terms of quantity Q. As with our analysis from the previous class, total cost in the short run consists of both fixed cost and variable cost. In this case, fixed cost is any portion of the total cost function that does not have a Q, whereas variable cost is any portion of the total cost that contains a Q. Notice here that our fixed cost is equal to 10 and the variable cost is equal to Q squared. Recall from the previous class that average total cost equals average fixed cost plus average variable cost. As such, ATC equals AFC plus AVC. We can calculate these cost concepts using our alternative cost equation using the same definitions discussed in the previous class. Average total cost is defined as total cost divided by quantity. Since our total cost function is Q squared plus 10, then average total cost is Q squared divided by Q plus 10 divided by Q, which is equal to Q plus 10 over Q. Average fixed cost is defined as fixed cost divided by quantity. Since the fixed cost is 10, then average fixed cost is simply 10 over Q. Average variable cost is defined as variable cost divided by quantity. Since the variable cost is Q squared, then average variable cost is Q squared divided by Q, which simplifies to just Q. Notice that our average fixed cost plus our average variable cost is 10 over Q plus Q, which is precisely what we calculated as our average total cost. Recall from the previous class that the calculus-based definition for marginal cost is the derivative of the total cost function with respect to Q. Since our total cost function is Q squared plus 10, then the derivative of Q squared with respect to Q is 2Q, and the derivative of 10 with respect to Q is 0. Therefore, marginal cost is 2Q plus 0, which is simply 2Q. Recall from the previous chapter that the short run is a time period in which managers can change the amount of workers, but the number of machines must stay the same. As such, we associated variable cost with the cost of workers and fixed cost with the cost of machines. In the long run, we allow the manager to change both the amount of workers and the number of machines. In other words, both the cost of labor and the cost of capital are variable in the long run. Indeed, there is no such thing as fixed costs in the long run. Recall from the previous class that the average total cost curve in the short run was U-shaped with its minimum point where it intersected the marginal cost curve. Since nothing is fixed in the long run, there is no longer a need to distinguish between average total cost, average variable cost, or average fixed cost, so we simply refer to average cost in the long run as the long run average cost. Let's take a look at the graphs for these average total cost curves in the next couple of slides. So how might we graph the long run average cost curve? Well, first we must now consider that the manager can decide not only how many workers to hire, but also how many machines to install on the production line. The differing values of workers leads to each short run average total cost, or SATC curve, being U-shaped, whereas each value of capital leads to a separate short-run average total cost curve. An increase in the quantity of capital leads to a new short-run average total cost curve that is shifted to the right. For example, if the pizza restaurant only has one pizza oven, then the short-run average total cost curve can be illustrated as SATC1. However, if the pizza restaurant acquires a second pizza oven, something that it couldn't do in the short run, now the new average total cost curve would be shifted to the right of the initial average total cost curve. This is because the higher fixed cost associated with two pizza ovens is initially spread over small quantities, leading to a higher average total cost. However, the advantage of a second pizza oven is that now the pizza restaurant could produce more pizzas than they could with only one oven, so larger quantities are now possible. Based on this figure, a manager that wants to target a quantity amount between 0 and Q1 pizzas would elect to have one oven. Whereas average cost would be lowest with two pizza ovens if the manager determines that the target quantity amount is between Q1 and Q2. We could then extend this logic if the pizza restaurant were to purchase a third or even a fourth pizza oven. The long-run average cost, or LRAC curve, is the result of the lowest short-run average total cost for each and every quantity amount and is represented by the blue line. The minimum efficient scale is the smallest quantity that leads to the lowest long-run average cost. In the slide here, notice that the minimum point of the LRAC curve is Q1, which implies that Q1 is the minimum efficient scale. However, this has been an EC 102 way of analyzing long-run cost. We will now use the constraint optimization technique to study this analysis with a more sophisticated approach. Let's revert back to calculating total cost in terms of capital and labor. Recall that R is the rental rate of capital, or the loan amount of buying pizza ovens, and W is the wage paid to each and every worker. Notice that our K does not have a bar over it like last class, because now we are allowing for the amount of capital to vary in the long run. Since the total cost C is equal to the fixed cost, R times K, plus the variable cost W times L, then we can rewrite this equation as K equals C1 over R minus W over R times L, which we can use to draw the Isocost line with the Isoquant graph that I introduced in the previous chapter. Let's take a look at the math I did here in more detail. If we have a particular cost target, C1, which is just a number, then C1 equals R times K plus W times L. We want to isolate K, so let's move WL to the left-hand side to get C1 minus W times L equals R times K. Next, let's divide both sides by R so that we can get C1 minus W times L divided by R equals K. We can rewrite this equation as C1 divided by R minus W divided by R times L equals K. Arranging the K to be on the left-hand side gets the final equation from the previous slide. K equals C1 over R minus W over R times L. Remember that the isoquant graph had K on the y-axis and L on the x-axis, where the curved isoquant represents the various combinations of capital and labor that lead to a particular quantity amount, Q bar. It is called the isoquant because iso means equal, so the curve represents different values of capital and labor that lead to an equal amount of quantity. As you can now imagine, the isocost line shows the different combinations of capital and labor that lead to equal values of total cost, and thus it is called the isocost line. Note on the graph that the y-intercept is C1 over R and the slope is negative W over R. If we set K equals 0, then we can solve for the x-intercept, which is C1 over W. Based on the previous graph, I hope that you caught the connection between isocost lines and budget lines, which we covered in Chapter 3 on rational consumer choice. The budget line showed the different amount of good X and good Y that the consumer can purchase that leads to the same amount of spending. Indeed, you can think of the isocost line as the budget line for the firm, where the firm's budget is a particular value for total cost, which we refer to as C1, and the two goods are capital and labor. As I mentioned in the previous chapter, isoquants are similar to indifference curves, which we covered in Chapter 3 on rational consumer choice. The indifference curve showed that different amount of good X and good Y that leads to the same level of utility or happiness for the consumer. As such, the consumer is indifferent between any point along the same indifference curve. In Chapter 8, we discussed how the isoquant is a convex curve in which the different points along the same isoquant leads to an equal amount of production. Remember that we used the constraint optimization problem to maximize a consumer's utility given his or her budget constraint back in Chapter 3. Graphically, we found that the optimal consumption bundle is where the indifference curve is tangent to the budget line. At this point, the slope of the indifference curve, which we called the marginal rate of substitution, is equal to the slope of the budget line, which was a negative value of the ratio of the price of good X to the price of good Y. Similarly, we will apply the same constraint optimization technique to the firm. However, instead of maximizing utility subject to the budget constraint, the firm will seek to minimize its total cost subject to its production function. If the firm really wants to minimize its total cost, it would simply hire no workers and buy no machines. This is not a fun example to study, so the production function serves as a constraint such that the firm actually produces a positive quantity. Graphically, we find that the optimal amount of capital, K star, and the optimal amount of labor, L star, occurs where the isoquant is tangent to the isocost line. At this point, the slope of the isoquant, which we called the marginal rate of technical substitution in the previous chapter, is equal to the slope of the isocost line, which we calculated a couple slides ago to be negative W over R. Notice that negative W over R is the negative value of the ratio of the cost of labor to the cost of capital. We will structure the cost minimization problem similar to the way that we structured the utility maximization problem. In this case, we want to choose the optimal amount of K and L that will minimize total cost, C, as a function of K and L, subject to a production function that guarantees a particular quantity of output, Q0. I will quickly go through the general constraint optimization problem and then wrap up with a numerical example. The first step is to set up the Lagrangian problem similar to what we did in Chapter 3. However, there are three major changes. First, we replace the utility function with the cost function. Second, the consumer's budget, which was just a number, is replaced by the target quantity amount Q0, which is just a number. Finally, the consumer spending portion of the budget constraint is replaced by the production function. The second step is to take the first order conditions. Remember, with the utility maximization problem, this meant that we took the derivative of the Lagrangian function with respect to x, y, and lambda. In the cost minimization problem, taking first order conditions means that we take the derivative of the Lagrangian function in step 1 with respect to L, K, and lambda. Notice that we set each derivative equal to 0 because we know that we've minimized a function when the slope is equal to 0. The first order condition with respect to L suggests that the derivative of the cost function with respect to L, which is just the worker's wage, is equal to lambda times the marginal product of labor. The first order condition with respect to K suggests that the derivative of the cost function with respect to K, which is just the rental rate of capital, is equal to lambda times the marginal product of capital. The first order condition with respect to lambda suggests that the firm produces the target quantity amount, Q0. This slide proves that the optimal amount of capital, K star, and the optimal amount of labor, L star, occurs when the slope of the isocost line, which is the wage of workers divided by rental rate of capital, is equal to the slope of the isoquant, which is called the marginal rate of technical substitution. If we divide equation 1, which was the first order condition with respect to L in the previous slide, by equation 2, which was the first order condition with respect to K in the previous slide, we get that the derivative of the cost function with respect to labor divided by the derivative of the cost function with respect to capital is equal to lambda times the marginal product of labor divided by lambda times the marginal product of capital. The lambdas cancel out, so the right-hand side is simply marginal product of labor divided by the marginal product of capital, which is precisely the definition for marginal rate of technical substitution from the previous chapter on production. If we define the total cost function as R times K plus W times L, as we did in the previous class, then the derivative of this cost function with respect to L is simply the wage, and the derivative of this cost function with respect to K is simply the rental rate. So the left-hand side of this equation is W over R. Notice the ratio of wage to rental rate is equal to the marginal rate of technical substitution, which means that we will be able to find K star and L star on the graph at the point where the isocost line is tangent to the isoquant. In order to actually solve for K star and L star, let's go through a numerical example. Let's suppose that we have a Cobb-Douglas production function, Q equals K to the 1/2 times L to the 1/2. The rental rate of capital is $4 and the wage is $2. Our total cost function is R times K plus W times L. Plugging in $4 for R and $2 for W, we get that the Lagrangian function is 4 times K plus 2 times L plus lambda times 2 minus K to the 1/2 times L to the 1/2, where the 2 that gets multiplied by lambda is given as the target quantity amount Q0. Next, we'll take the first order conditions and set the derivatives equal to 0. First, let's take the derivative of the Lagrangian function with respect to L. Notice that the derivative of 4 times K with respect to L is 0. Notice that the derivative of 2 times L with respect to L is 2. Notice that the derivative of 2 times lambda with respect to L is 0. And notice that the derivative of negative lambda times K to the 1/2 L to the 1/2 is negative lambda times 1/2, which is the exponent for L, times K to the 1/2 times L to the negative 0.5, because we're taking the 0.5 power and subtracting 1. Let's set all of that equal to 0. Now let's simplify to get that the first order condition is 2 minus lambda times 1/2 times K to the 0.5 power times L to the negative 0.5 power, which is equal to 0. Rearranging so that it's just 2 on the left-hand side, we get that 2 is equal to lambda times 1/2 times K to the 1/2 power times L to the negative 1/2 power. Let's refer to this equation as equation 4, which we will use in a couple slides. Next, let's take the first order condition with respect to K. Notice that the derivative of 4 times K with respect to K is 4. The derivative of 2 times L with respect to K is 0. The derivative of 2 times lambda with respect to K is also 0. The derivative of negative lambda times K to the 1/2 L to the 1/2 becomes negative lambda times 1/2, which is taking the exponent for K and putting it down, times K to the negative 1/2, because we're taking the exponent for K, which is 1/2, and subtracting 1 to get negative 1/2, times L to the 1/2 power, and we're going to set that all equal to 0. Simplifying, we can get that 4 minus lambda times 1/2 times K to the negative 1/2 power times L to the 1/2 power is equal to 0. And isolating 4 gets us 4 equals lambda times 1/2 K to the negative 1/2 power times L to the 1/2 power. We'll refer to this equation as equation number 5, which we'll refer to in the next slide. The third and final first order condition is with respect to lambda. Notice that the derivative of 4 times K with respect to lambda is 0. The derivative of 2 times L with respect to lambda is 0. And that we have that the derivative of lambda times 2 minus K to the 1/2 power L to the 1/2 power is simply 2 minus K to the 1/2 power times L to the 1/2 power. We'll set all of that equal to 0. We'll simplify to get 2 minus K to the 1/2 L to the 1/2 equals 0. Isolating 2, we get that 2 equals K to the 1/2 L to the 1/2, which is simply our production function set equal to our target quantity amount, which is equal to 2. Let's refer to this equation as equation 6, which we'll refer to in the next couple of slides. The next thing that we want to do is take the first order condition for labor, which was equation 4, and divide that by the first order condition with respect to capital, which we refer to as equation 5. We'll do this in order to get labor in terms of capital. So notice that equation 4 was 2 equals lambda times 1/2 K to the 1/2 power L to the negative 1/2 power, and equation 5 was 4 equals lambda times 1/2 times K to the negative 1/2 power times L to the 1/2 power. So dividing those two equations, we get that first line, which is 2 over 4 equals lambda times 1/2 times K to the 1/2 power L to the negative 1/2 power, divided by lambda times 1/2 times k to the negative 1/2 power times L to the 1/2 power. Notice that the lambdas and the 1/2 cancel out on the right hand side, so that we can get that 2 over 4 is equal to k to the 1/2 power times L to the negative 1/2 power divided by k to the negative 1/2 power times L to the 1/2 power. We can simplify that right hand side to get that 2 over 4 is equal to k to the 1/2 power minus the negative 1/2 power, which is combining the k's in the numerator and in the denominator. We'll multiply that by L to the negative 1/2 power minus 1/2 power, which combines the L in the numerator with the L in the denominator. We then get that 2 over 4 is equal to k to the 1 power, which is just k, times L to the negative 1 power, which is 1 over L. So that 2 over 4 is equal to k over L. Moving L to the left-hand side and simplifying for 2/4, which is the same thing as 1/2, we get that 1/2 L is equal to k. And finally, to isolate L, we get that L is equal to 2k. Let's call this equation 7, which we will refer to shortly. Now that we were able to use the first order conditions for capital and for labor in order to get an equation for labor in terms of capital, let's use the first order condition with respect to lambda in order to get another equation in which capital is in terms of labor. So the first order condition with respect to lambda was 2 equals k to the 1/2 power times L to the 1/2 power. Again, this was just saying that the target quantity amount, which was given to you as 2, is equal to the production function, which was given to us as k to the 1/2 times L to the 1/2 power. Notice that k to the 1/2 power times L to the 1/2 power is similar to square root k times square root L. And the way that we want to get rid of square roots is by squaring both sides. So what we're going to do in the next row is take the square of both sides. So we've got 2 squared, which is equal to 4, times k to the 1/2 power times L to the 1/2 power squared, which is simply k times L. Isolating k, we can get that k is equal to 4 over L. We'll refer to this as equation 8, which is used in the next step. We're going to plug in equation 7, which was our equation for L in terms of k, into equation 8 to get k star. Recall that equation 7 was that L is equal to 2k. So we're simply going to substitute 2k in for L in equation 8 in order to get that k is equal to 4 over 2k. 4 over 2 simplifies as 2, and let's move the k in the denominator on the right hand side to the left hand side to get k times k, which is k squared, so that we have k squared is equal to 2. Therefore, our k star is equal to square root 2. Now that we have a numerical value for k star, let's plug that into equation 7 in order to get L star. Remember that equation 7 was L equals 2 times k. Since k star is equal to square root 2, then L star is equal to 2 times square root 2. So your final answer is that k star is equal to square root 2 and L star is equal to 2 times square root 2. In order to check our work, it's nice to plug in k star and L star into the production function and make sure that we get the target production amount, Q0, which was initially given to us as equaling 2. Given that our production function is k to the 1/2 and L to the 1/2, then plugging in square root 2 for k and 2 times square root 2 for L gets us square root 2 to the 1/2 power times 2 times square root 2 to the 1/2 power. Now let's be careful here with the exponent. So square root 2 is the same thing as 2 to the 1/2 power. So we're taking 2 to the 1/2 power and taking that to the 1/2 power. With 2 times square root 2, remember, square root 2 is 2 to the 1/2 power. So 2 times square root 2 is 2 times 2 to the 1/2 power, but we're going to take all of that to the 1/2 power. Given the rules of exponents, 2 to the 1/2 power to the 1/2 power is the same thing as 2 times 1/2 times 1/2. Whereas 2 to the 1/2 power becomes 2 to the 1/2 power. Since 1/2 times 1/2 is equal to 1/4, or 0.25, then what we get is 2 to the 0.25 power times 2 to the 1/2 power times 2 to the 1/4 power. Since everything is base 2, then we can sum up all of the exponents to simplify, so that we get 2 to the 1/4 plus 1/2 plus 1/4, which is equal to 1. So we have 2 to the 1 power, which is simply 2. Notice that this is indeed the target quantity amount. Now that we're done with Chapter 9, you're fully prepared to not only complete Homework 4, but also take Exam 2.